Imagine it is the year 2050. A severe drought has hit, and water supplies are drying up faster than anyone predicted. How will a human farmer react to a crisis like this, one they've never faced before? To answer difficult questions like this, scientists use agent-based models. Think of these as incredibly detailed life simulation video games, but built for research instead of entertainment. Inside these models, programmers create thousands of digital agents. Each agent follows a specific set of behaviors. Depending on inputs like rainfall levels or market prices, the digital farmer makes individual choices, like deciding whether to plant corn or switch to a drought-resistant crop. The goal is to see how these individual choices add up across a whole community. By running these simulations, researchers can safely test real-world policies and survival strategies before a crisis ever reaches our actual farms. But this brings up a tricky dilemma. If a computer is predicting an event that hasn't happened yet, how do we prove its answer is actually reliable? Usually, we check predictions by looking at the past, but with a brand new challenge, like a severe climate shift, the way farmers acted 10 years ago is no longer a useful guide for how they will survive tomorrow. The future often breaks the patterns of the past. That means we cannot look at historical data to grade our model's homework. We need a different way to check if these simulations are on the right track. For a long time, the standard way to test a model was to look backward. Scientists would take historical records and see if the computer's final results matched what actually happened. This process of output matching is known as empirical validation. This split-screen chart shows how well a model might match past data points on the left. But relying on this method in a changing environment is like testing a student who memorized all the answers to an old exam. Once a brand new variable like a climate shock is introduced, those memorized answers become useless. Since we can't rely on the past, researchers focus on the internal logic, the rules and gears that drive the simulation. Ensuring the inner structure is realistic is a process called structural validation. When facing an uncertain future, a model earns its trust by having the most realistic set of internal rules, rather than simply spitting out a number that matches the past. To make sure these internal rules are sound, a team of researchers developed the Keep It Adequate, or KIA, protocol. This document serves as a master scientific checklist. This flowchart maps out a modeler's choices, linking design to real-world problems. First, define the exact question with just enough detail. Next, ensure digital agents act like flawed humans, not rational robots. Finally, track the unknown, testing different settings to ensure robust results. This protocol shows that reliability depends entirely on context. A model is valid only when its specific methods are carefully matched to its specific purpose. A computer simulation does not have to be a 100% perfect mirror of reality to be scientifically useful. Creating a perfect copy of the real world is impossible. A simulation simply needs to be adequate for the specific job it was built to do. The true power of the KIA protocol is transparency. It forces scientists to document every choice they make and every rule they write, opening it all up for others to double-check. These strict protocols transform a computer program into a scrutinized, trusted virtual sandbox, a tool to help navigate tomorrow's realities with evidence instead of guesswork.